Hi! In this video, we will give an overview of a fairly new algorithm which solves the single source shortest path problem. The paper describing the algorithm was published in 2023 and was written by Jeremy T. Fineman. The algorithm solves the SSSP problem in soft O of mn to the 8/9 for graphs with negative edges, where n is the number of vertices and m is the number of edges in the graph. Here you can see an example of an input graph where negative edges are represented in the color red. The algorithm can be broken down into two major parts. First, the algorithm starts by eliminating negative edges by reweighting the graph over several rounds. As you can see in the animation, the number of negative edges decrease for each round of elimination. When there are no longer any negative edges left in the graph, the algorithm proceeds by running Dijkstra's algorithm on the graph in order to find a shortest path from S to all other vertices in the graph. The most interesting part of Feynman's algorithm is the elimination rounds, where he reweights the graph several times. But before diving further into this, Feynman makes some simplifying assumptions about how the graph input should look. The first simplifying assumption assumes that every negative vertex only has one outgoing edge. Feynman defines a negative vertex as a vertex which has a negatively weighted outgoing edge. Here is an example where a negative vertex has more than one outgoing edge. In this case, we split the problematic vertex in two and add an edge between. The weight of this new edge is given by the formula you can see above, and the weight of this new edge is then subtracted from the weights of all the outgoing edges in order to preserve distances. The second simplifying assumption assumes that every vertex must have a degree of at most big O of m divided by n. Here's an example where this simplifying assumption is violated. For this graph, the number of vertices is 10 and the number of edges is 11. In this example, you can see that there's a problematic vertex, which has an out degree which is too large. To reduce the out degree, we introduce two new vertices and assign each of them half of the outgoing edges. If the degree of the newly introduced vertices still does not satisfy the constraint, we simply repeat this procedure until satisfactory. For an arbitrary input graph, both of these simplifying assumptions can be satisfied by a simple graph transformation done in polynomial time. As mentioned earlier, the algorithm completes several rounds of eliminating the negative edges before it proceeds by running Dijkstra's algorithm. We will now take you through a single round of elimination, which can be broken further down into four parts. Firstly, the algorithm begins by reducing betweenness. Then, it finds either a negative sandwich or a one-hop independent set. If it finds a one-hop independent set, then it eliminates the negative vertices immediately, or else it proceeds with the negative sandwich by making the sandwich R-remote. Lastly, it eliminates the R-remote edges by a technique called hop reduction. In this video, we will show animations for the first and fourth step of the algorithm. First, the algorithm does the betweenness reduction. In broad terms, the goal of this betweenness reduction is to ensure that there is an upper bound on the number of vertices in between any two vertices in the graph. Here you can see an example of an input graph. To reduce betweenness, we start by randomly sampling a subset of vertices in the graph. This subset is denoted by the letter T and are represented by the yellow vertices in the example. For each of the vertices in T, we compute the h-hop distance to the vertex from all other vertices in the graph and the h-hop distance from the vertex to all other vertices in the graph. H-hop distances is a recurring concept in Fineman's algorithm, and an h-hop distance is the distance from a vertex to another using only h-negative edges. After we compute the h-hop distances, we construct an auxiliary graph. In the auxiliary graphs, all vertices from the input graph remains. For the edges, we add an edge from each vertex in T to all other vertices in the graph, and from each vertex in the graph to all vertices in T. As you can see, when we construct the auxiliary graph, it really quickly becomes quite convoluted. Because of this, we will iterate using a much smaller example. This is an example of an input graph, which is a lot smaller. Now we want to reduce betweenness for this given graph. As before, we begin by sampling a subset of vertices. For this graph, the subset of T will be of size 2. As it is a random sampling, any 2 vertices in this graph can be part of this subset, but let's say that for argument's sake, vertex 0 and 5 was included in T. As before, for each vertex in T, we compute the h-hop distance to that vertex from all other vertices in the graph, and from that vertex to all other vertices in the graph. To compute these h-hop distances, we use an algorithm which is a hybrid of Bellman-Ford and Dijkstra's algorithm. We call this algorithm Bellman-Ford-Dijkstra, or BFD. BFD runs by alternating between relaxing positive edges using Dijkstra's algorithm and relaxing negative edges using Bellman-Ford's algorithm. This alternation between Dijkstra's algorithm and Bellman-Ford's algorithm is done h times. So, to compute the h-hop distances from vertex 0 to all other vertices, we begin by running Dijkstra's algorithm. Each time an edge is relaxed, it's indicated by the green flash, and then the corresponding value is updated in the dist array. After running Dijkstra's algorithm on the positive edges, we run Bellman-Ford's algorithm on the negative edges by relaxing each of them exactly once. Then we again run Dijkstra's algorithm on the positive edges. Now we have computed the h-hop path from vertex 0 to all other vertices in the graph. This is then done for all the vertices in T. Now we can construct an auxiliary graph H, where the weight of the edges is the recently computed h-hop distances. Finally, we compute a price function from the auxiliary graph, which we want to reweight our initial graph with. To compute this price function, we insert a supersource and connect it to all vertices in the auxiliary graph. From there, we compute the h-hop distances again to each vertex using BFD. Phi denotes the price function, which we just computed, and as you can see in the table, these are the values for each vertex. When the graph is reweighted in phi, we have now reduced betweenness with high probability. In the second step of the algorithm, we either aim to find a negative sandwich or a one-hop independent set. If a one-hop independent set is found, we aim to eliminate the negative edges straight away. This is done by computing another price function, again by inserting a supersource and running BFD. On the other hand, if we find a negative sandwich, a little more work is required. This entails step 3 of the algorithm, which is reweighting the negative sandwich in order for it to be R remote, which is done by reweighting the graph in yet another price function. Now we arrive at the fourth and last step of Fineman's elimination algorithm, which is the R remote edge elimination by the technique called hop reduction. Here's an example of an input graph which contains a negative sandwich. A negative sandwich consists of 3 things: two vertices that make up the crust, which is denoted x and y, and a set of negative vertices, which makes up the middle of the sandwich, denoted u. At this point, we want to focus on eliminating the negative edges going out from u. So for convenience, we remove the other negative edges from J. From this graph, we again insert a supersource and compute the h-hop distances using BFD. Based on these distances, we construct an auxiliary graph H, which contains different layers of vertices. The blue vertices are one layer and the white vertices are another. The numbers of layers in the auxiliary graph depend on the number of hops used in supersource distances, but for this example there are only 2 layers. In this auxiliary graph, we again compute the supersource distances by inserting a supersource and running BFD in order to compute another price function which can be seen on the screen. Reweighting the graph in this price function successfully eliminates the negative edges going out from u, while still preserving the distances in the original graph. This concludes one round of the elimination algorithm. As mentioned previously, this elimination algorithm is run several times in order to eliminate all negative edges. After this is done, Dijkstra's algorithm is then used to compute a shortest path. This concludes our animation of Fineman's algorithm. Thank you for watching.